peaks or two troughs. Thank you, Rachel. Okay, we got is our wavelength. The distance between two peaks, for instance, would be our wavelength. Okay, so that's illustrated here on the slide. You can see I have two lines that are on the exact same point on the peak. And the distance between those is our wavelength, right? And that is presuming here that our x-axis is a distance axis, which is usually how we talk about waves. Okay, we can also talk about another term with waves, and that is called frequency. And that's the number of wavelengths that'll pass at a given point in a certain amount of time. Okay, this one's a little bit weirder, right? But if you just think about what the word frequency means, how many times, right? How often? Okay, and so you can think about the fact that a high frequency wave is going to pass a given point more often than a low frequency wave. Okay, and we give a special unit that we'll often use called hertz. That's 1/seconds. You may have heard that one before, especially our musicians in the room. You know 400 hertz is it's a good note, right? All right, so then our given symbol for frequency is going to be nu. Okay, so we have terms that we're going to use. Our amplitude is A, capital A. Our wavelength is going to be lambda. That's this Greek symbol here. And then our frequency is going to be nu. Okay, so look at these two waves over here. Which one has a larger wavelength?
The second one.
The second one. Yes, the one on the bottom, right? It has a longer distance between the two peaks when comparing them directly with each other. Which one has a larger nu frequency?
The first one.
The first one. Yeah, you might have to use your imagination a little bit and say, okay, I got a point right here. And if these two waves move across the screen at the same rate from left to right, which one is going to have more peaks hitting that point in the same amount of time? So the frequency of the top one is larger. The wavelength of the bottom one is larger. And we see here our relationship between frequency and wavelength. It's an inverse relationship. The one does one thing, the other goes the other direction, right? So if one goes up, the other goes down, and vice versa. This is going to be important to keep in mind because scientists have a habit of using a whole bunch of different, whether it's frequency or wavelength or some other term, you have to convert between them in your head. So keep that in mind, that frequency and wavelength are opposite in direction. One goes up, the other goes down. That's an inverse relationship. Okay, so here's a cool fact. Electromagnetic radiation all travels at the same velocity, the speed of light. 3.00 times 10 to the 8th meters per second. By the way, for all of you, I'd love for you to take notes by hand. I will also post these slides after we're done. They'll be up on the Canvas site for you to look at. But take what you think is the most important off of these slides and put it right there on your paper. Okay, interestingly, because we can look at our units, we've got meters per second. Okay, and I also remember that per second is also hertz. That's my units of frequency. So I've got wavelength. That's how far it goes. That would be in meters. And I have frequency. That's the per second, how fast and often something happens. So speed is equal to wavelength times frequency. Look at that. We got meters over seconds. That's what I just explained. We can boil that down into a simple equation. The speed of light, which we're calling c here, is equal to its wavelength times its frequency, lambda over nu. And if I have units of meters for wavelength and hertz or per second for my frequency, then I have an end unit for my speed of meters per second, which is a typical physics unit for speed. This is great, but there's another way to remember this. What's nu? Hey, Rachel, what's nu?
C over lambda.
C over lambda, right? We rearrange our equation, divide both sides by lambda, and we get frequency equals the speed of light divided by the wavelength. What's nu? C over lambda. That's the way you can remember this equation forever, and you'll be able to rearrange it and use it in whatever way you need. Okay, so when we say electromagnetic radiation, what are we talking about? We're talking about radio waves, microwaves, infrared, visible waves, all these kinds of things. Okay, we can even put them on a scale. Looks like this. This is one version of the scale. Okay, so when we think about light, we're usually thinking about this teeny tiny region right here in the visible. Okay, that's the light that we can see. Maybe think a little bit about ultraviolet light. You've heard of that. It gives you a sunburn. Infrared light, we've heard of that. You can use that for night vision, or you can use it to heat things up. I have an infrared lamp in my chicken coop right now, keeping my chickens warm. Okay, but all of these other things, including microwaves, the stuff in your microwave, the thing you use to heat up your tea or whatever, that is also light, or better term would be electromagnetic radiation. Okay, the stuff that I am coming to you via, right? I got this microphone, which is wirelessly transmitted to that doohickey over there, which is then wirelessly right? That's all radio waves, radio frequency stuff. A little bit of microwaves now too, some of the gigahertz regions. Anyone's heard of 4G, 3G? The G has to do with gigahertz. That has to do with where it is on this spectrum here. Anyway, light is super important. I'm getting a little distracted. We also have X-rays. X-rays are the things that you get an X-ray image done with. That's going to be also electromagnetic radiation. So there's tons of this around us, and we use it all the time. So we really need to understand it. And as chemists, specifically, we're going to use it in a particular way. Here's another image with some of the same stuff. Look at all the sources down there.
You're muted.
How did that happen? How long have I been muted for?
About 30 seconds.
Oh, nuts. That was weird. Better now? Okay. As I was saying, we've got ionizing radiation up here, ultraviolet, X-ray, and gamma rays. Those are ionizing, meaning they're strong enough, they have enough energy. In other words, their frequency is high enough, right? As we look, we can see this wave down here kind of telling us what happens with that wave as we go across. And in fact, our frequency increases as we go to higher and higher energy electromagnetic radiation, and our wavelength decreases as we go to higher and higher energy radiation. And at those very high energies, 30 petahertz and higher, I guess it's shown on this chart, we get enough energy that we can take electrons out of compounds, right? We call that ionizing radiation. The light bumps into electrons and knocks them off into space, and you're left with ions. This is why you can't get too many X-rays. This is why we can treat things like cancer with radiation. And this is why you don't want to handle those gamma ray sources. Very dangerous. But it's important to keep in mind that relationship between frequency, wavelength, and the amount of energy something has. Okay, another property of waves that we're going to need to talk about to understand the chemistry that we're about to get back to, I promise, is wave interference. This is a cool graphic I have of two waves, the blue wave and the green wave. And I hope you can see that. It's the two with the same exact amplitude. Track those for just a moment as you watch and kind of try to ignore that red line. Okay, you'll see they're moving in opposite directions from one another, right? The green and the blue are moving apart. And then you can watch the red wave, which is actually adding the green and the blue together. So if we look at the very center of the chart, you can see these points. We have the blue and the red kind of bouncing up and down. And you'll notice that the red always stays right there in the middle, because as blue goes up, green goes down, and they stay put. But as the waves come into phase, as we call it, which means that as the peaks and troughs line up with each other, we get increased amplitude of our red wave. And as they go out of phase with one another, we see that they kind of cancel out, right? And they go to zero. And at one instant along this kind of animation, we can actually see that that red line goes perfectly flat, right? The two waves cancel each other out perfectly. This is called interference, and you can have constructive or destructive interference. What we see here is kind of both of those happening kind of on and off. Constructive interference is when they add together to get a higher amplitude than their initial amplitude. Destructive would be when they cancel each other out and they wipe each other out. Okay, two examples of that are shown right here. Okay, so this leads us now to a new theory. You've heard of quantum mechanics before, and we need to get into that now in this class, because we had classical mechanics, works great for apples and macroscopic objects, this ladder that they brought in. That's all classical and makes sense. But when we start thinking about light, right? So far, all the stuff I've talked about light makes sense. We have this continuum of electromagnetic radiation, and it has all these possible wavelengths and frequencies and energies and all of that. And that works fine, but it starts to break down. We have an observation, okay? And that observation is that when I heat up some burner or something like that, it eventually starts to give out light, right? Some of you may have seen a burner like this on an old hot plate or an old stove top or something like that. Or maybe you have one of the glass top ones, and you always see it turn red, right? As it heats up, it starts to turn red. What happens if you put iron into a forge and get it really, really hot? You start pumping the bellows, right? And it turns white hot, and then you can smash it down and shape it and stuff like that. Anyone know what I'm talking about? Okay, so that is called black body radiation. And as you heat stuff up and it gets warmer and warmer and warmer, it starts to glow, and it's glowing hot, white hot, we might say, okay? But something weird happens there, because if you track the color of light given off by a hot object and you plot it against temperature, you get a cool plot, okay? But if you track that plot and you keep going and you say, all right, what if we got super duper hot, hotter than we can actually get? Then what happens? Well, we would expect that eventually you can heat stuff up hot enough that it will start to emit X-rays, okay? So they called this the ultraviolet catastrophe back in the 1800s, because they didn't even see it going into the ultraviolet. At some point, all of that emission from hot objects called black body radiation stops increasing in its energy. And that is counter to what we would think based on heating things up super duper hot. Okay, long story short, if light is just a wave, it's not going to work, and it's not going to explain why objects glow when their temperatures increase. Okay, so light can't just be a wave, because there must be something else going on here too. Okay, so let's pause here for just a moment on our slides. I'll stop my screen share. I'm gonna move on to our next section. We're gonna do a couple of practice problems where we start working with calculations, all right? So I'm gonna go over to Chem 101, and we'll break you into your breakout groups from last time. Does everyone remember what group they are in? Give me a message in the chat if you need help on which group you are in. Look at that. Rachel's on it. Rachel, you're a champ. Appreciate it. All right, so today we have a, oh no, Chem 101 did not save the activity. That's okay, I got practice problems. Let's do it right here. I'm gonna go ahead and post 2 slides from PowerPoint onto Canvas. So we'll do it the old fashioned way. We got 2 practice slides. Those will show up on Canvas momentarily. And what I want you to do is go into your breakout groups, open these up in Canvas, work together and see how quickly you can get through these. But it's not about quickness. See if you can get through it together. All right, I'll have these up in just a moment. Sorry about that, everybody.
Did we go ahead and open the breakout rooms?
That sounds good. These should be up on Canvas anytime. Feel free to ask for help with the Ask for Help button.
Go forth. Anybody see the breakout room menu? No? Okay, we'll try again. All right, how about now?
Unfortunately, the way PowerPoint translated my slides, it put the lowercase l instead of the proper font, which would be symbol, which would turn that L into lambda. So you had to do a little extra digging in your notes. 640 nanometers equals our lambda. That's our wavelength. Say you didn't know wavelength was lambda. You do have a hint, right? We can always look at our hints for nanometers. That's all right. DMart's getting there. We're almost there. You can just do the whole board if you want. Perfect. That's perfect, DMart. Thanks. Okay, so 640 nanometers, that's a length, right? A nanometer is a unit of length. Wavelength, it's right there in the name. So that's perfect. By the way, this does not show up backwards for everybody, does it? Just for me on my screen?
It's right for us.
Wonderful. That's good news. Best news I heard all day is this. Okay. We also have our equation. What's new? Who am I looking at? What is new? What's new? What's my
C
equation?
over lambda?
C over lambda.
C over lambda. Hey. If you were all here in the room with me, I'd make you like chant it with me, but you're not. So we get Zoom. And the question asks us, what is the frequency? What is the frequency in this equation?
New.
New. This one. That's our frequency. Okay, so frequency, wavelength, and that gives us C. What is C?
Speed.
C is what?
Speed.
Speed, specifically a
Of light.
a special speed, the speed of light, which is a constant that you could memorize. 3.0 times 10 to the 8th meters per second. Okay, so that gets us started. Our equation, thanks to our little mnemonic device, is in the exact right order. We need to solve for frequency. We've got to plug in our values for speed of light and wavelength. We know wavelength up here, so let's do it. Nu equals 3.0 times 10 to the 8th meters per second divided by 640 nanometers. Ruh-roh. Now my units aren't going to work because I've got meters up here and I've got nanometers down there. We can handle this though. We have tools. It's called dimensional analysis. We can do that down here at the bottom of the arrow. We just have to be, or the bottom of the equation. We just have to be a little bit careful when we punch it into our calculator. So 640 nanometers, there are 10 to the 9th nanometers in every 1 meter. So that will be our conversion factor. And now we can plug that all in. You can take 640 divided by 10 to the 9th. You'll get a number. It'll be something like 640 times 10 to the minus 9th. And then you can divide the speed of light by that number. And if you do, you'll get a number that's kind of wild. Your frequency here is 4.68. And I'm going to do significant figures in a moment. So I'll just take a bunch of extra digits. 4.6875 times 10 to the 15th hertz. Hertz is the same as this per second up here, because the meters will cancel and our nanometers will also cancel. Okay? For significant figures, we had 2 significant figures on this measurement of the speed of light. So what I'm going to do is leave this number like that, but put a bar over the top of the 6 to let me know that that's the significant digit, and I shouldn't keep the ones after it. That's one way you can do significant figures. Do it all at the very end. Okay, do we have questions?
I do. Why do we multiply by 1 over 10 to the 9th?
Right, because if I look at my units, and I hope you can read this okay, I've got meters per second up here, but down here when I had my wavelength, it's in nanometers. And I need my units to work out appropriately or else they're not going to cancel. So I have to make sure the units will cancel out. So the nanometers, I cancel out with this dimensional analysis, leaving me with meters here, which cancels with the meters in our speed. Another way to do this would be to convert the speed of light into nanometers per second, which would be a very big number. Rachel, did I get the wrong answer?
Yeah, you're off by an order of magnitude. At least according to breakout room 6, who I was with.
All right, give me a thumbs up emoji if you think if you punch this into your calculator and you got 10 to the 15th. Uh-oh. It appears I'm on an island. Oh, Abigail is going straight for the thumbs down. All right, Abigail. You win. 10 to the 14th. I must have punched it in my calculator wrong. I'll double check that and then I'll post it again. Mike, you got a thumbs up. Oh no, did you get 10 to the 15th? No. Okay, cool. All right. Should we do the other
I
one
got
too?
10 to the 14th, Graham. Sorry.
All good. I have no problem being wrong. This is why we work in groups as scientists. Then we don't crash our spaceships this way. Got to double check all the work. Okay. So in the interest of time, I will not go through the second problem, but I will post a solution to Canvas for the second practice problem because we have something more interesting than that practice problem. If you're interested, the answer is 4.072 meters. Really quick, I do have to talk about this. The practice problem was this one. Project this again. All right, so this practice problem asks you to calculate the wavelength of radio waves with a frequency of 93.3 megahertz. Anyone got a radio station that's 93.3? I don't know what the Appleton one would be, if there is one. I should have used one that I know, the Avenue, 91.1. But anyways, I didn't. But this is really interesting because the answer we get to this is 4 meters or so, which when you think about it, explains something that you might have observed in real life, which is that these antenna for our broadcasting, our radios, are huge, right? They're really long. And if you've ever looked at the antenna on a car, old cars used to have really long antennas. Now they're coiled up wires, which are also long, but now they're in a coil. And the reason for that is that the wavelength of the signal coming out of the radio or over the radio is about 4 meters, and you have to be able to catch a decent portion of that electromagnetic wave. So I think that's pretty neat. Rachel says she got 3.2 meters also. So anyway, close enough. Same order of magnitude, good enough for now. I'll post the actual solutions up on Canvas. In the meantime, let's do something more fun. Go over here and put on my lab coat. So one of the questions that you might ask yourself is, why are we bothering with all of this outrageous light stuff? See if I can see myself over here. No, this is good. Okay, so one of the reasons we need to look at this light stuff is going to be right here. I'm hoping this is going to work. I haven't done this demo before, but I'm excited. So DMart's going to control the camera. He's going to hit the lights, and I'm going to light some stuff on fire. So I got my flame retardant lab coat on. I got some glasses in case the glassware gets too hot and blows up. I don't expect either of those things to happen. And I've got here 6 beakers. They all have a different metal salt dissolved in them. I've got sodium chloride, potassium chloride, lithium chloride, barium chloride, strontium chloride, and copper chloride. And what we're going to do in those solutions, they are dissolved in water and ethanol mixture, which is enough ethanol to be flammable. So I'll use my torch here and start a flame in each of these beakers, I hope. Too much water. All right, potassium's going. All right, so I have my flames. Can we see those? Needs to be darker. Okay, here we go. They're going to need to get hot. And as they heat up, I'm going to do something else. I'm going to also dip one of these sticks into some water and then into some actual salt of these different salts. And I'm going to skip straight to the really good ones. All right, so as you watch, and I hope you can see this okay, feel free to speak up. You should start to see some interesting colors form. There we go. There we go. Anyone seeing these colors? What do you think, D-Mart? Do we need to go darker lights? You can turn the lights all the way off if you can.
We can see them.
How's that? Is that any better?
Now we can't
This is
see.
great in person. All right. So I don't know how well you can see from there, but sodium has a nice bright yellow color to it. That's this one on what I think is on your right. So the far right here. Now you can see the color on that lithium flame. That's a beautiful, vibrant magenta color. Copper's not doing what I want. There we go. If I stir up copper a little bit, you can now see the beautiful green color of the copper. Strontium is occasionally flashing up that pretty red color. There we go. Get barium going again. Barium's bright yellow. Okay, so that's great. That's working, but we need to go one step further here. And to do that, I want to take what is called a spectrometer. I can see that these are different colors of lights, and I hope that you can too. I think especially the lithium flame, this bright purple one is obvious. Strontium is pretty cool also. And then copper, when I give it a good stir, turns that nice green color there. There we go. All right, and unfortunately, my laptop timed out and disconnected from the wireless. So we'll have to do away with this. Okay, so what I would do as a scientist normally is to take these flames and realize that there's information in the color of these flames, right? These flames are telling me something about the compounds involved. I've got lithium, which is this bright purple color. Barium is yellow. Strontium is another kind of reddish purple. Copper is, for some reason, this green, right? And each of these colors is going to tell me something about the atoms. But color, the name, right, is a little bit arbitrary. It's a little human. Philosophically thinking, we might say that that color is, you know, different languages have different numbers of colors of blue, for instance. So as a scientist, what I want to do now is I'm going to take some instrumentation or some way of specifically telling me what colors of light I'm going to do. And we just talked about for nearly 50 minutes exactly how we could do that, right? Color is associated with wavelength or frequency of the light. And because of that, we can go ahead and then use that light color information. We could measure the wavelength of these different colors of flames, and we can get information about some energies and what's happening with the energies here. So those are starting to burn out. I think that's going to be sufficient for that demonstration, a little rainbow of flame. We'll hit the lights back on. I'm going to take this lab coat off. We'll let those burn out on the bench. Any questions about what you just saw? Does that all make sense? Oh, thanks for the chats. Okay, so I'm going to go ahead and discard that jacket. But the mystery here, another way to look at these wavelengths is to now go back. Here we go. All right, so here's another mystery for us. Another way to look at these flames would be to get what's called a prism. Some of you have heard of a prism. It's just a shaped piece of crystal that spreads out light rays. So looking at this graphic I have here on the slide, looks like the Dark Side of the Moon album cover from Pink Floyd. What an album, great album. But what we also see is what happens with this prism is as the light hits the edge of the prism, it changes. It's something called the index of refraction. It's actually going to change the speed at which that light comes through based on its wavelength. And that spreads out the wavelengths from one another. Okay, so it diffracts them across. So we actually see a spectrum. If I have a perfect white light coming from some hot object, that black body radiation, that's going to go ahead and spread out into this beautiful rainbow, like you see here, the white light spectrum. Okay, if I use a helium lamp, and the way a helium lamp works is I put helium gas in between two electrodes, and I use the electrodes to create an electrical voltage that heats up the helium essentially and makes it nice and hot. What I see from that when I spread it out through a prism or a diffraction grating is very different from the white light spectrum, right? So white light would be coming from a hot object. Light coming from a helium lamp has discrete specific lines, just like this. Okay. In the same way, if you looked at those flames that I just lit on fire in the middle of our room, you would see specific lines showing up through your prism. A barium lamp has a spectrum that looks like this. We did have barium, right? We did. Barium was the reddish colored flame, and you can see lots of orange. Orange is probably better, right? Lots of orange lines here on that barium spectrum. So those are the brightest lines. That's the one that we saw with the flame. And specifically, in the temperature of the flame that was burning is important here too. We'll see different lines with different temperatures. You do an oxygen lamp, oxygen has different lines as well. So all of these were a great mystery to people in the 1800s and the early 1900s, trying to figure out what was going on. But when you start to think about the fact that light has specific energies, the most mysterious, the weirdest part about this is that we don't have like bands. We don't see kind of, a section of this spectrum or something like that. We see lines, sharp, bright lines. Okay, so that's really interesting. What does that even mean? Rhetorical question. No one has to feel like they have to answer that. Okay, and there was a theory that came out of this to answer this. And that new theory is quantized energy. Okay, so they're thinking about black body radiation. You get an object hot, it has a big kind of broad spectrum of light that it shows. But then when you do it a certain way, you see something totally different, right? If you burn a specific ion, or you have a lamp like a helium lamp, a neon lamp, you see sharp specific lines. Okay, Max Planck came by and said, I got a way to describe this, but it's weird and it doesn't make sense to me, you guys. Just go with it. We're going to call it quanta, okay? And so this is an important concept for us as we start discussing atoms and their structure. Okay, Planck proposed that a quantum of energy is related to its frequency, and where we're used to continuous energy in our macroscopic world and with classical physics, we need to think of a place like this where energy can only be in certain chunks, right? It has to be in something called a quanta. It's like a shoe size, right? Shoes come in 10, 10 and a half, 11, at least here in the United States, right? I wear a size 11 usually. Honestly, I probably wear something like a size 10.8, but that doesn't exist, right? There's no continuum, there's only specific sizes. Okay, and what Planck also said was that the frequency of light is related to how much energy it has. And there were experiments that he used to confirm this. Okay, and then the extra important idea here is that when you think of these quanta, there are these integer multiples that come out. When you actually measure the wavelength of the light and the energies of the light, and then you look at the relationship between them, you see we get these integer multiples. So like here I've got h nu, that's one energy, and then 2 times h nu, 3 times h nu, etc. Okay, he got a Nobel Prize for this theory in 1918. Spoiler alert, electrons do this too. And that's what we're going to get into, right? When we're talking chemistry, we're talking electrons, and electrons are also quantized. Super important for us, but we're getting there. Okay. Another interesting thing that comes out of this quantum theory comes from Einstein, and that is something called the photoelectric effect. We've already kind of thought about this. Okay. Photons, when they hit a piece of light or piece of metal, can emit electrons, but only if they have the right energy to them. You've got to get a certain frequency of light to hit that metal plate to actually eject electrons. If the frequency is too low, there's not enough energy, those electrons stick to the metal surface and they can't come out. Okay, and they have to be exactly right. So this is the experimental setup that Einstein used. You can find this in the textbook, so I'm not going to go into it in super detail, but you can collect your electrons in this vacuum changer. I'm pointing at the screen like that's helpful for you, right? So we have a metal plate here. There's nothing inside. We evacuate it with a vacuum. Okay, and then we put a positive terminal over here with a battery over it. Then we can see how much current flows. And as long as you have the right wavelength of light, you can actually see those electrons jump from the metal plate across the vacuum to hit that positive terminal. You can see that on your current indicator. Okay, and the energy packets have to have a specific energy, just like Max Planck said. Okay, This is cool. It's also interesting to note that's what Einstein won his Nobel Prize for, right? Was this photoelectric effect. In other words, light turning into electricity effect, not for relativity. E equals mc squared is something different. That's pretty interesting. Okay. So light has a wavelength, but it also comes in packets with energy proportional to frequency. We can put these equations together. We get energy equals Planck's constant times the speed of light divided by its wavelength. Okay, and then you get into this weird thing. Well, okay, so if they don't have mass, is light a particle or is it a wave? And why do we think they don't have mass? Well, if they're a wave, waves don't have mass. Like, what is the mass of a wave in the ocean? I don't think you could tell me that, right? The wave is the actual water going up and down, and that has no mass. But the photoelectric effect and all of this E, energy, things that have energy have mass also, right? We know that from Einstein as well. So this is weird. These two equations should not go together, and somehow they do, because, and that gets us into this weird question. Photons don't have mass, so is light a particle or is it a wave? And the answer is yes. It is both. This is a paradox called wave-particle duality, which you might have heard about. So with that, I'm gonna stop for there. We'll go back over some of the important things that we talked about, right? We talked about stop my share here. We talked about properties of a wave. We talked about wavelength. I think, yeah, good. Okay, we talked about wavelength. We talked about frequency. We discovered two equations. Nu equals c over lambda, and E equals h nu. Okay, these are two equations that are really important as we go forward. Okay, we did a little bit with units and dimensional analysis, and we saw one important point here, which is that light energy is quantized. And that's where we'll pick up on Friday, and we'll get into the quantum nature of electrons. So we'll go from there. I'll stick around for 5 minutes. I got to go to first year studies after this, but hope you enjoyed the demo. We're going to try that again in person at some point, but hopefully you could see it pretty well. It was fun. It was fun here. I can tell you that much. All right. Have a great Wednesday, everybody.